you what the definition of decoding, what the definition of list decoding is and what we are going to prove today. So let's zoom in a little bit and see what each one of these things said. So list decoding simply said that your decoder will consider a received message, received vector, which is a corrupted code word, and output up to L different messages. And we want it to be successful by saying that the correct message that we transmitted is amongst the decoded set, provided what you sent was the encoding of your message and what you received was at distance at most epsilon from this thing. So this is what it means to correct epsilon fraction errors with lists of size L. Okay. So we want all of these things to be algorithmic when possible, which means both the encoding and decoding functions should be algorithmically computable. And the result we will prove today is quite very, very strong. Okay. It says that you get to specify some, fudge parameter delta. Okay. So last time we were drawing these graphs, which said, okay, here is the rate of error. Here is the rate of the code. And we proved a limit saying you cannot get up to this line or beyond this line. And delta today is going to be just basically measuring our distance from the line in some sense. Okay, so it says how far from this line do you want to be? And we'll get you that. So you get to choose any delta which is positive. You get to specify what is the fraction of errors you expect. And that fraction of errors can be corrected with lists of polynomial size. We won't care about what the list size is. And the rate that you will get is more or less optimal. 1 minus epsilon, except for this delta, this is optimal. Okay, so it's really on this line, except it's a delta below this line. And what's the dependence on delta within the poly in N? Great question. I will not address it right now. We are going to assume delta is constant, and we are going to give codes for N, which is going to infinity. Another question that you could ask is, okay, what is the alphabet with which we are working? It's going to be a large alphabet. It is actually going to depend not only on N, like in the Reed-Solomon codes, but even on N to the power of 1 over delta and things like that. So it's going to be the encoding and decoding functions are going to be over some alphabet of the form, are functions of the form E maps sigma to the sigma to the K to sigma to the N. And size of sigma, which we'll often denote by Q, is like N to the 1 over delta squared. Maybe, we might be allowing things of this type. So I will not follow the dependence on delta, but even achieving this is remarkable. We have gotten better results, and I might mention it later. But today's goal, by the way, it's not such a densely packed talk as yesterday. So I hope to go over the code slowly and present most of the decoding analysis, except for some tedious details, tedious and really boring details, which I will not do. So what is the code? The code is basically the same code as the one that we worked with yesterday, Reed-Solomon codes. The only thing we will do to them is to do something called folding, which is really not algebraically profound. It's going to be, we'll see what it is like. So here's what the code looks like. You'll pick a field element gamma and n distinct field elements, alpha 1 to alpha n in FQ. Actually, I will want the following thing. I will want gamma to the j alpha sub I to be all distinct in a certain range for I and j, but let me get to that later. So these will all be considered distinct. And what am I going to do? What is the encoding? A message is going to be still a polynomial of degree at most k. Okay, the message will be associated with a polynomial. The degree of that polynomial is at most k. And its encoding will be evaluation at alpha 1, gamma times alpha 1, gamma squared times alpha 1, and so on up to gamma to the m minus 1. Oops, there's two different m's in this page. So let's just call this message P. Okay. So m is going to be another integer which specifies the code. And I will take many, so not only evaluated at alpha 1, but also gamma times alpha 1, alpha gamma squared times alpha 1, and so on up to this thing. And then move on to alpha 2, and there'll be another block of things for alpha 2, and so on. Okay. So as described here, this is just the Reed-Solomon code. I just happen to choose a set of points which are of the form gamma to the j alpha sub I for various choices of I and j. Okay. So far, this is not a new code. Here's how we're going to make a new code out of it. We're going to put all of these things and put them in a single block and call it a single letter of the alphabet. Okay. So M symbols of FQ are now a single letter of the alphabet. So our sigma is no longer FQ, but it's rather FQ to the M. And so our code maps FQ to the K to sigma to the N, or equivalently sigma to the K over M to sigma to the N. Okay. But that's all I've done. I just decided that all of these things are one element. Why is this significant? Recall that our definition of Hamming distance says an error here is counted as an error in the whole block. Once you've decided to make an error here, you are charged for an error in the whole block. Okay. So whether you make an error here or an error and an error here and an error here, it's all the same thing. It's one error, but it's one big error. And we are going to require you to make at most some epsilon fraction of n errors, which means the number of blocks that are going to be touched by your error is epsilon fraction. This makes a difference. It is not as if you get to touch epsilon fraction of these little things, but epsilon fraction of the whole thing. By the way, this is the same notion that we had with Reed-Solomon codes. You could have looked at P of alpha 1 as a collection of bits, but we counted it as an error if any one of the bits was errors. Now we are working with these folded Reed-Solomon codes. Folding simply refers to this fact that we are working with a bunch of symbols of the alphabet put together. And now we are going to call this one letter of the alphabet, that's one letter of the alphabet, and so on. Okay. Is the code clear? That is the error correcting code. We are going to pick gamma and alpha i's so that the gamma to the j alpha i's are all distinct. And we now got a code which maps like that. Okay, questions? Feel free to type questions into chat or unmute and ask. All right, so that's the code. What we are going to prove is that you can decode from a large fraction of errors. N over m plus 1 plus m over m plus 1 times k is the, that's the number of non-errors that we want. So this is the number of places which will not be in error. All the remaining can be in error. How should you think of it? Think about what happens as m slowly grows. This portion that depends on n is getting less and less and less relevant. So this is like an, delta times n it will become, or delta over 10 times n, etc. This part is getting closer and closer to k, but k is necessary, right? I mean, if I want to convey k symbols of information to you, you should at least receive k symbols right. The only catch is actually the number of symbols that are correct over here is supposed to be k over m. Okay, our new k is k over m, but this is actually the real, the degree of the polynomial k. So this is not actually achieving capacity at all. It is factor of 1 over m away from capacity no matter what you do. So if you're making m large, then it sounds like this is pretty bad. But here is what will happen. We will prove that you can actually decode from this code, provided just the alpha 1 to alpha n are distinct. Okay, and there'll be some other conditions on gamma having large order and so on, but never mind that. The only thing we care about is really that alpha i's are distinct. So you can actually use the, gamma times alpha 1 might equal alpha 2. Or gamma squared times alpha 1 might equal alpha 3. Things like that. These are allowed. And this realization that you can actually work, provided just these things are distinct, will allow us to go from here to actual capacity achieving. So to achieve capacity, I would have really liked to see divided by m over here. I don't have it yet, but I'll get very close to dividing by m in the next slide. Okay, so this is the lemma that we will shoot for and try to prove later. But first, let's look at this and stare at this number and see how to improve it. Okay, all we need is the alpha 1 to alpha n are distinct. Okay, all right, great. Here's what we're going to do. We started off, we have this code, we'll use some m prime. We will use this code with parameter m prime, which is very large, maybe like 100 m. Okay, much larger than our original budget. So we will get a code which is over this very large alphabet, 100 times larger in the length than we were planning for. What we will do is we will look at this thing and say, oh, I have a block of m things over here which are good. Let's write that down here. Now let's look at this overlapping block of m, just has one different element, and write that as a second element. Let's look at the next overlapping block of the m, write that as a third element, and keep doing this as long as these blocks of size m are not overflowing. So I cannot go there. So I'll stop when I reach here. How many such blocks can I write down given one such block here? Well, I have 100 m symbols here, and I'm moving, writing windows of size m and moving them up one at a time. I can write down 99 m symbols like this. Okay, that's almost m prime. That's 0.99 m prime symbols I've written down here. Okay, and so each one symbol over here is mapping to 0.9 m prime symbols of the Emory code. And now I'll just apply my lemma to this sequence that has been obtained this way. Now, if epsilon fraction of these symbols are in error, how much fraction of these symbols are in error? Still exactly epsilon. As a fraction, nothing has changed. One error here will translate to 99 m errors there, but the length of this whole thing was 99 m larger. 99 m plus 1, yes, you can get one more symbol. That's exactly correct. So I will not look at that plus 1. In fact, many plus 1s will be ignored. Okay, great. So indeed, that's telling you that you understand what the code is. Great. Okay, and you understand what is this reduction. So we want to decode this code, but we will convert this. This is the code that we are working with. But for the decoding, we'll pretend that this was actually a code word of this other code, which had m, which was 100 times smaller, but much longer. It's now longer by a factor of 99 m. And the decoding algorithm applied to this these numbers, when applied to this new code, will be great, will be good for the original code. Okay, so that's the plan. All right, so with this slight switch, we are back to this simple lemma that we want to prove. Okay, the code is given by picking these alpha 1 to alpha n distinct, gamma 1 to, so that, and then we are looking at this gamma times alpha 1, gamma times square times alpha 1, and so on. And that's the first block, and we are back to m. These numbers will suffice for us. Okay, all right. So this is what we're going to design an algorithm for to prove this lemma. So repeating the lemma statement here, we have an evaluation of a polynomial p at alpha 1 to alpha n, gamma times alpha 1 to gamma times alpha n, gamma square times alpha 1 to gamma square times alpha n, etc. And we want to decode. What are we going to do with this? So let's first write down the decoding problem. What do we have? This is parameters of the code. Okay, you're given k, n, m, etc., gamma and alpha 1 and so on to alpha n. These we determined before the message was chosen. So once the message is chosen and transmitted, you transmitted p of gamma times alpha 1, P of gamma times gamma square times alpha 1, and so on. There were M symbols here. What you received may be beta 1, beta 2, and so on up to beta sub n. And either the whole symbol is in error or everything is correct. Okay. And we are getting many such symbols. Now what we want to do is to find all polynomials whose degree is at most k, which have the feature that if you look at the number of coordinates I, such that for every one of these entries here, you are getting P of gamma j to the I equals beta sub I of j. Okay, so each one of these symbols equals P of gamma j to the alpha I. Okay, and if that number is larger than this quantity that I will call D from now on, capital D, mk over m plus 1 plus n over m plus 1. So recall, this is where we are getting our mileage from. As m becomes larger and larger, this is looking more and more like k, and k is good for us, n is not good for us. N is saying I want everything right. K is saying I only need as much as the roughly the message length right. And we are moving towards this side, so that's good news. Okay. So as long as we can recover from so many errors, I mean, as long as the number of errors is number of agreements, number of places where the equality holds is at least so much, we will be able to find the polynomial P. Okay, so this is the decoding problem. And now we need to give you the analysis, the algorithm and the analysis. Okay, is the problem clear? All polynomials P in one variable which have this agreement. Okay, and questions are welcome at any stage. So here's the entire algorithm. Well, there's details missing in each part, but here's what we're going to do. So last time when we were recording Reed-Solomon codes, we said, let's find a polynomial in two variables. X corresponded to the alphas and Y corresponded to the evaluations of the polynomial. The reason we are able to do better now is because we have many variables we can associate with each one of these rows. And the more variables we have, the better it is for our degree bounds. This degree gets, the agreement bound gets better and better. So how is it, what are we going to do? We're going to make it, in fact, a very simple polynomial. Okay, Q is a function of m plus 1 variables, and x, which represents the original x, and y1 to ym, which correspond to the m different evaluations that you have for every alpha. We will find a polynomial Q, which is 0 on all the given points. So for every I in 1 to n, Q of alpha I, beta I sup 1, beta I sup 2, and so on to beta I sup m are all 0. So if you look at any one of these columns and you evaluate, you have m plus 1 values here, you put Q on this, sorry. If you put Q evaluated at this point, that's 0 for every point. Okay. How many constraints did we come up with? Well, we came up with n constraints. How many unknowns do we have? Well, it depends on the structure of the polynomial. And now we're going to look for a very simple polynomial. Yesterday, when we were doing this, we said, oh, we'll have terms of the form y squared and y cubed and so on. None of that today. The only terms are of polynomials in x and polynomials in x multiplied by y sub I for some I, some j, y sub j for some j. So a0 plus y1 a1 plus y2 a2 plus ym am, that's our polynomial. I need to make sure that we have at least n degrees of freedom here. Okay. So how do I get n degrees of freedom? Well, I'll divide it equally over all the polynomials. That gives me n over m plus 1. And then I'll reduce the budget here a little bit and increase this one a little bit till I get the right thing. So turns out the choice we will choose is we will make sure that the degree of A0 is at most this quantity D. And the degrees of AI are at most D minus K. Right? Why this choice? Eventually, I expect to plug in y1 equal to p of x, ym equal to p of gamma to the m minus 1 x. As a function of x, these are all polynomials of degree k. And when I multiply the two, I will get polynomials of degree d, and the whole thing will be some polynomial of degree d. Okay. So degrees of AIs are at most d minus k. Degree of A0 is at most d. And find me such a polynomial. Okay. That is step one. Now, what are we going to do with this polynomial Q? We are going to look for all polynomials capital P which satisfy Q of x, P of x, P of gamma x. See, we expect the first row is P of x. The second row is, this is P of x. This is P of gamma x, right? This is P of gamma x. And this is P of gamma to the m minus 1 x, and so on. So let's plug in those things and find me all polynomials such that this identity holds. Okay. Is the algorithm clear? At least the two steps of it should be clear. You should feel free to ask if something is unclear. Either I'm not being clear or something I haven't said yet.
Sorry, might be a stupid question, but like, so P might not be unique, or is it unique?
Okay, great. P may not be unique. That's good for us because we are trying to do the list decoding problem. So we will find all P's and output them all. Now, further questions arise. Q may not be unique. And we said, don't mind, doesn't matter which Q you will find, we will use it in the second step and it'll be fine. Good enough. Now comes the good aspect. This is probably what you were asking. How do I know that there is any limit to the number of P's? Maybe every polynomial P satisfies this equation. How do we know that? So we have to prove something. We have to do some analysis. We also have to completely specify the algorithm. Step one, we've seen this yesterday. How will we solve step one? We will just look at the coefficients of AIs are unknowns. So, but we have linear constraints in these coefficients. These are homogeneous linear constraints in these coefficients. We'll just solve the linear system and we'll know that. How many P can we have? Again, another question on chat, same answer. At the moment, we don't know. We have no idea how many P's we're going to have. This is what we have to control. Okay. All right. So step one, I think most of us believe, linear system, big linear system, and why is the degree of yi in Q only 1? We are going to look for a Q. Yeah, so these are conditions on my Q. Find Q such that this is true, that is true, and that is true, and that is true. Okay, so these are all constraints we're imposing. And we can ensure these constraints easily by saying, okay, look, the unknowns are the coefficients of the AIs, and we'll solve for these unknowns and find. Okay, great question. All right, so that's the Q we are looking for. Because the number of unknowns we will choose will be more than n, such a Q will exist, and we will find it one such Q by solving a big linear system, and we are done. Okay, all done, polynomial time, this is okay. How are we going to solve this problem? How are we going to bound the number of P's? That's where the challenge is, and let's go on and look at it. So let me, even though I've said these things, let me repeat it in the analysis. So a Q as we require it in the step does exist, and it can be found. Why does it exist? Because the number of variables, the coefficients of A0, coefficients of A1, and so on to coefficients of AM, that number is of the form D plus M times D minus K. Maybe there are plus ones and so on, but it's all in our favor. And that number is greater than N. So this is what we will ensure. And that's really how we chose this quantity. Okay, I want this to be D, this to be D minus K, subject to the condition that this equality holds. So the solution to this equality is that. Okay, so Q exists. Q can be found algorithmically, yes, because it's a linear system. For every Q, and this is something that we didn't, that I haven't said so far, but now we're going to claim this. For every Q that you find, if P is a solution where there is lots of agreement, then we will have that Q of X, P of X, P of gamma X, and so on to P of gamma to the M minus 1X is 0. So, you know, there were really multiple things that we needed to say. This algorithm is going to find a P such that this condition holds and output it, or find all such P's and output it. We need to say that if there is a good P, one which actually solves this condition, that will be included in this set. We need to say that this step can be done fast. And the set that we output over here is not exponentially large. Of course, the two go hand in hand maybe, but you know, we have ways of expressing exponentially large sets using polynomial time algorithms. So I don't want to cheat. So really, we need to make sure that the number of P's that satisfy this condition is small. And we'll prove all of that, but let's start by saying, why is this P included in this list? So we have some polynomial P, and P satisfies P of gamma to the J alpha sub I equals beta sub J of I for many I, for DI. Okay, or D plus 1, maybe some, you know, there may be some plus minus ones here that I'm ignoring, but you can fix that later. So we know that this is true for many choices of I. Why is this P going to satisfy this condition? So let's go look at it. So let's look at the polynomial called R of X. This is, by the way, basic algebraic geometry applied in such a basic setting that we don't think of it as algebraic geometry, but this is really what's going on. We have a polynomial in many variables. We are doing substitutions of many of these variables with some simpler variables. It's like intersecting a curve in m plus 1 dimensions with many other curves in m plus 1 dimensions. And when you take all these intersections, you get a univariate curve. Here it's all explicit in front of us. So let's look at Q of X, P of X, P of gamma X, and so on to P of gamma to the M minus 1X. This is a polynomial in X. What is its degree? It's at most D, because we chose A0 to have degree at most D in X. And all the other terms are such that when I do this multiplication of this with A sub I will get a degree D polynomial. Then I add a bunch of degree D polynomials, I still get a degree D polynomial. So degree of R is at most D. But now if you look at an index I of the type that we are looking for, where beta 1I equals P of alpha I, beta 2I equals P of gamma alpha I, and so on to beta Mi is P of gamma to the M minus 1 alpha I. All these identities are holding simultaneously, which is what the power of this folding does. We know all of these identities hold together. Then by our definition, if I look at Q of alpha sub I, beta sub I1, and so on to beta sub I M, this is 0. This is how we found our polynomial Q. But beta sub I equals P of alpha sub I, beta sub thing equals P of gamma alpha sub I, and so on. So this is really saying that Q of alpha I, P of gamma, P of alpha I, P of gamma alpha I, and so on is also 0. But this is the same as saying the polynomial R of alpha I is 0. Right? So a few steps compressed into one, but it basically says every time you have this equality and agreement, R has found a 0. If the number of zeros is more than D, then R must be identically 0, which is exactly what we are looking for here. Okay. Questions about this part? This is the part that we did not do yesterday when we were doing Reed-Solomon decoding. We didn't prove that, you know, the solution is going to be right and so on. Here we are proving it. There's nothing left out in this stage. So If you have questions, now is a good time to ask questions. Questions, thoughts, anything? So suppose you pick alpha 2 to be gamma times alpha 1. Then you have, in fact, indeed, we are doing that, right? I mean, we were originally planning to do this whole thing so that all these blocks are distinct. But then after we did that conversion, we got this second element here is the same as the first element here. But notice that this is a different polynomial. This is a different root of the polynomial R. Okay, it's a completely different root of R. So an error will be counted as 99M errors. And if you had, so if you had an error in this big M prime size block, and then when we convert it, we're going to get lots of errors, 99M prime, but the fraction of errors has not changed because it's, we took one block and wrote it as 99M blocks. And so the ratios have been preserved. Okay, great. Okay, now comes the thing, how are we going to find these P's? And miracle, this is more, I mean, it's the same, but it's sort of, this is the reason why Rani's question, earlier question, why did we ask yi's, our solution to be linear in the yi's? Well, here is a second reason to, I mean, the analysis does get simpler, but this part is very crucial. We can now just say, oh, look, substitute unknowns for the coefficients of P, and you have one big linear system which says, find me those coefficients, okay? This is just a linear system in the unknowns. So if P of X is summation is C0 plus C1X plus so on up to C sub K minus 1 X to the K minus 1, then what we have is a big linear system in C0 to CK minus 1. Okay. So no factorization of polynomials today. You know, when you're factoring linear polynomials, it's not really factorization. You're just doing some linear algebra. And that's what we're doing today. So nothing profound about this step, at least algorithmically, nothing remarkable. Okay. So now the question is the number of such polynomials P small? How many polynomials P are we going to find? Well, this also tells us the answer. It is really the dimension of this linear system, because there's going to be some big linear system that you're going to set up. And the solution is a linear subspace. The dimension of that subspace counts the thing. If the number of solutions is small, because we're working in FQ, is going to be of the form Q to the power of the dimension. Okay, so we want the dimension to be constant so that we can claim that the number of solutions is polynomial in M, polynomial in the input length. Does that make sense? So this is to be done, and this is all that is to be done. So let's see if there are any questions about the analysis so far. So we've gone back to this algorithm. First step is obviously polynomial time. It's one big linear system. Second step is another linear system. I mean, this is quite stunning. This is so simple in some senses. And all we now want to do is, well, make sure that this linear system does not have too many zeros. Okay. By the way, I'm going much faster than I was expecting to, so definitely feel free to stop and ask questions and so on. I have just 3 more slides and okay. But if we have lots of time, we'll just jump over to lecture 3 and start talking about that. What I thought would be lecture 3 is going to become lecture 2. Okay, any questions at this stage? Okay, can step 4 be done using Berlekamp-Massey? I don't know. The honest truth, yeah, this Berlekamp-Massey is a sort of a miraculous algorithm, does all kinds of remarkable things, but at the end, we are just solving a linear system. So I'd rather just focus on the fact that it's a simple linear system. Linear systems can be solved, and it's easier to believe this will be done. Okay, there are variations of some other things that could be useful. I don't know that you need Berlekamp-Massey for this. All right, so now step 5. What are we going to do? I mean, I'm not going to go, this is the one step where I'm not going to do the full detailed analysis, but I'm going to give you enough so that if you have the patience, you should be able to go home and do the analysis yourself. There's some tedious details where I will not tell you what is the linear system, what is this thing. What does a linear system look like? Well, if we say P of X is this polynomial, you know, that's my vector of unknowns. I'm going to have some matrix M. Its entries are functions of what? It's functions of alpha, beta, gamma. That's it, right? Alpha i's, beta I sub j, and gamma to the power of various different things. And that polynomial is, so that determines this matrix, also determines a vector. And we now want to solve M times this vector equals to B. Now, this matrix is not totally arbitrary. It turns out it's actually upper triangular. So it actually looks like 0 below the diagonal and something else above. Or maybe, I mean, depends how I wrote the rows and columns. It's either upper or lower triangular. It doesn't matter. I'll call it upper triangular. Okay. So this is kind of very useful. Okay. Because if I look at this row and this times this, it's saying that, well, you know, the only thing that affects this row is C0. And then I would just need to set C0 up so that this equality holds. And then the next one is, you know, I've already fixed C0, next one will determine C1. And then the next row will determine C2, and so on. Why is this matrix turning out to be upper triangular? It's not, shouldn't be too much of a surprise. Let's just look at our condition. We want to say Q of X, P of X, P of gamma X, and so on to P of gamma to the M minus 1 X is 0. Okay. If this is to be 0, it should be 0 mod X, should be 0 mod X squared, should be 0 mod X cubed, etc. It's an identity that holds all the time, so it should hold modulo X to various powers. When I look at it modulo X, will C1X, will the coefficient C1 make a difference? It doesn't, because that's already affecting only the nonlinear terms in X. And we're only interested in the constant term. So C1, Ck minus 1 do not affect this condition mod X. When I go mod X squared, only C0 and C1 make a difference. But each one of these equalities gives me one linear constraint. And that's where this upper triangular system comes from. Okay, so it's a very simple upper triangular system. Upper triangular because it is this. And recall, upper triangular means this is 0, this is something, and this is arbitrary. Okay. Now, when you have an upper triangular system, the solution should be unique if the diagonals are all non-zero. Okay. If you have a, you have a square matrix times this thing, and your diagonals are non-zero, then there is a unique solution. But are our diagonal entries 0 or not? Maybe they're all 0. And then we're in trouble. Maybe half of them are zeros. Then again, we are in trouble. So what are we going to do? It turns out, when I look at the diagonal, a constant number of these entries could be 0, but the rest of them will be non-zero. So that's the main advantage. That's the main result over here. Okay. So why is that the case? It turns out, okay, by the way, we have to choose the matrix, the polynomial Q a little carefully for this. If Q happens to have a divisor, which is some polynomial in X, we will not allow it, okay? We will insist that Q cannot be divisible by any polynomial. So no polynomial f of X divides Q of X, y1 to ym, okay? Right, I mean, so this is a polynomial in m variables. There is no reason that there should be, and we are looking for factors which are specific settings of y's. Using a polynomial f of x which divides all of q is not going to help us with that. So if we ever find it, we will just factor it out and then use this lower degree polynomial. And if you're wondering, oh, we don't want to do factorization, that's fine. Just use the lowest degree polynomial q that satisfies the conditions that we had from before, and that lowest degree should not have an f of x dividing it, because if it was dividing, you would divide by f of x and get a lower degree polynomial. So we're going to assume, so let me write that down just because I didn't. So no f of x divides q of x y1 to ym. So, you know, when I have yi's as the formal variables, f of x does not divide. If I put y1 equal to p of x and y2 equal to p of gamma x, etc., no conditions. F of x won't if f of x be the GCD of ai's of x? Yes, Ranin, you're totally right. I think you would, or the GCD, yeah, exactly. So if we don't want to do factorization, but you're willing to do GCDs, that's also totally okay. So right, so we don't have to, we just won't allow any common factors among the AIs, and that's easy to enforce. So this is the only assumption. Once we have this assumption, it turns out that all of these entries, the diagonal entries that we have, these are actually very nicely structured. Okay, in this part, I'm not proving or I'm not writing it down, but I'm making a claim which you should verify on your own if you're curious. These entries are all of the form. So this will be B of gamma. The next one will be B of gamma squared. The next one will be B of gamma cubed, and so on, where B is some fixed polynomial of degree m. So B depends on alpha, beta, etc., everything, and the coefficients of Q maybe, but it's a polynomial, and it's the same polynomial being evaluated at different values of, you know, so gamma, gamma squared, gamma cubed, and so on. Okay, it's a polynomial of degree m. So how often can these things be zero? Well, as long as order of gamma is greater than k, and this is a k by k matrix, all these are distinct. Anytime I find a zero here, that's a root of B. And once again, we use for the nth time in these lectures, the fact that a univariate polynomial of degree something, in this case m, has at most m distinct roots. So our m is chosen to be about a constant. And so the number of such roots is constant. And so that tells you that this linear system cannot have too many solutions. Okay. How can we be sure that B is not a zero polynomial? Great. So that is exactly what relates to this condition, it turns out. Okay. So when you look at B, it turns out that B is somehow related to the GCDs, etc., etc. So it will turn out to be that if Q of x does not have a single polynomial dividing the whole thing, then B will not be the zero polynomial. Okay, so it's another detail that I'm not verifying, mainly because, you know, writing it down will ask me to write down some complicated linear equations, which, you know, are obvious but kind of boring. Okay, so that's how it turns out that we do this analysis. Okay, So once again, why does this mean that we have a small list size? Every time you have a non-zero diagonal entry, it says, given the choices of all the previous things, the next choice of CI is uniquely determined. When I have a zero entry, it's conceivable that all the possible values of CI will satisfy this linear equation. Okay, either all of them will or none of them will. If none of them will, it was not a satisfiable system. We're happy. The number of solutions is zero. If it turns out all possible choices of CI could be satisfying this, that's Q possibilities. But the number of zeros is at most M. Number of solutions we will find this way is at most Q to the M. Okay. So, and all the solutions lie in a nice subspace. So this is how the solution worked. Okay. So that tells us that the number of solutions is at most Q to the M, and we are done. Okay. So that concludes folded Reed-Solomon codes and their analysis. It may have been a bit fast for those of you who've seen it for the first time. I'm more than happy to repeat any of these points. If not, I will move on to other topics and tell you what else we were going to be looking at. Any questions at this stage? Isn't Q of x equal to 0 mod x to the I a weaker constraint than Q of x equal to 0? Yes. So in particular, so we use that constraint only to notice that the system is going to be diagonal. It turns out that because of the way this system is set up, you will never see polynomials of degree greater than D. Okay, so once I have up to this, so the left-hand side is obviously a polynomial. This is obviously a polynomial of degree at most D. And so if I say this is 0 mod x to the D plus 1, that actually is equal to the original constraint. Did that help? So did we choose gamma to be a generator or not? No, we just need gamma to have large order. And by the way, I did not specify what order is, but order is just that gamma to the 0, gamma to the 1, and so on up to gamma to the k minus 1 are distinct, right? That's all we are saying. So this much we need. We need order of gamma to be large, which means this collection of entries are all distinct. And we'll need a few more conditions of this. The gamma times alpha to the i's are all distinct. Okay. Gamma to the j's times alpha to the I are all distinct. Where does the polynomial b come from again? Okay, good. So I didn't tell you how to express this condition, q of x, q of x, q of x, p of x equal to 0. How do you write this condition? You write down unknowns for the coefficients of p, write down coefficients of these polynomials and coefficients of, you're given q. So you'll write down all of these things, and then this will give you one big polynomial whose coefficients are all known for each degree. It's a polynomial of degree d. So this is the same polynomial that we called r of x here, right? Except, this polynomial r of x, except we have unknowns for the coefficients of p. So it's going to be some huge polynomial. X to the I will have some coefficients for each value of I. And these coefficients are going to be linear forms in C0 to CK. When you write down this whole linear system in that form, and you convert it to the form where we say, oh, there is a big matrix, M times C0 to CK equals something, all of these entries are going to be arbitrary polynomials in alpha I, beta ij, gamma, and any coefficients that you found of these polynomial q. Okay, you found coefficients of q, they're all going to show up. They're all going to sit here and populate all of these entries. And each one of these is going to be some entry in all of these things that we are including. When you look at these entries and you say, oh, this depends on alpha I and beta j and gamma sub and other such things. Well, it depends on all of them, but it's the same polynomial applied to different gammas that actually turns out to be. You can write that entire thing as one simple polynomial b, which captures all the dependence in alpha, beta, gamma, etc., alpha, beta, and the coefficients of q, everything. Only thing that remains is gamma, and that will vary from row to row. And b of gamma turns out to be this thing. So it requires inspection of this matrix. This matrix is not, profoundly insightful, at least not to me, to inspect, but yeah, you can do it. And then once you inspect it, it turns out that's what it looks like. Okay. By the way, I mean, we've been trying to demystify this algorithm a little bit, and we have some recent papers on it, which tells you, how generally will this work and so on. Some of you might find it helpful. Okay. All right. So that's all the. Can you repeat how we get the trade-off between delta and the size of the alphabet? And can we hope to reduce the size of the alphabet? How did you know these questions? Here we have. Okay, so, all right. So yes, we can. And let me tell you a little bit more. So reminder, up to now, we were not being explicit, but now let me be a little bit more explicit. So epsilon and delta are given in constants. And now you can pick whatever, however large an n you want, but it has to be sufficiently large. It can't be too small. And then we're asking the question, okay, so there is, we want to pick an alphabet and a list size, both of which are going to be polynomials in n, but these polynomials depend arbitrarily on epsilon and delta. In particular, delta is the worrisome thing. Epsilon, is the factor of error, let's say 50% or 10%, whatever you want. But this depends, now the alphabet size depends on n in some pretty bad way. And then there's encoding functions and decoding functions, and that tells you that you are actually epsilon L list decodable. Okay, that's what we have just proved. So we proved all of this except for this structure of B business, but really everything else is there. And by the way, you could say, here is a error correcting code. I mean, folded Reed-Solomon codes are not hard to express. You can ask the question, what is its list decodability? We know now, based on what we just proved, that this is epsilon L list decodable, that, you can get such good polynomial size lists will give you very good error correction capacity. The only proof I know is the one that I have, or the only types of proof that I know are these types of proofs, the ones that we just gave. There was a little bit more complex proof of this, and it's been simplified a little. But look, this proof is entirely algorithmic. There's no combinatorial proof of this combinatorial statement. If I just said, I don't care how fast the encoding function is, and in particular, I don't care how fast the decoding function is, one could hope for maybe a simpler proof, maybe a purely combinatorial proof, or maybe some algebraic proof, which is somewhat more direct. I have none of them. It's really the only proof that I know is this algorithmic proof. And these are the first codes that we know that come this close to capacity. These are the only codes we know that are this close to capacity, explicit codes. And they actually come with this algorithm, and the algorithm is the proof that these come so close to capacity. Okay. Now turning to the question that was asked by Andre. Can you make the alphabet smaller? And the answer is yes, you can actually make the alphabet smaller. It can be made a constant which depends only on delta. And this was in the original paper which introduced the folded Reed-Solomon codes by Guruswamy and Rudra in 2006. So yes, we can actually get the alphabet down. This involves an idea like concatenation. So you build a code over a large alphabet and then somehow reduce the alphabet size to binary, or not binaries, to something smaller. But this is where the analogy stops. The analysis and the intricacies of that composition are actually immense, and it comes from an paper. It uses a much earlier paper of Guruswamy and indic. So they showed us how to reduce alphabet sizes without, in some senses, compromising on error correction ratios, the gap to capacity, and that very sophisticated composition is needed. But I mean, it's something that I have given as exercise, as a problem with many parts in my class, and people are able to solve it. It does require lots of little details that you have to follow and sophisticated ideas. So this Q actually does not need to be polynomial in n. It can be made constant. So you can actually put the Q here. Okay, it doesn't depend on n. Same thing is true, it turns out, about the list sizes. And this took us even longer to realize. If I'd realized I had so much time, I would have tried to put in the proof of these folks in this talk. Koparthi, Ranzui, Saraf, and Wouters, in the last 2 or 3 years, I think they proved that you can actually make the list size much smaller. And along the way, they actually give even simpler algorithms for doing some of this decoding part, though it does use the original, the analysis that we just did. They at least use that analysis, even if they don't use the same algorithm. Okay. So by now we know that actually both of these quantities can be moved here, and the only dependence on the alphabet on the length is the length of the code and the rate and so on. So great. So these two can both be done. Each one uses very different sets of ideas and ideas that we will not cover here. So, and now comes towards the next lectures. Maybe I will, I might get started on the next lecture today, but let me ask what was the questions that what I thought would be the next lecture would be asking. So can we go down to the binary alphabet? Okay. Rani is also asking, can we get both of them together? Yes, actually, the two things go well together. Once you get down the list size to be small in the outer code, you preserve it in the inner code. So that's good. Yeah, it's good. It also okay, I should mention, okay, maybe I'll just take an aside since we have the time. Let me tell you about a related problem. Actually, though I claimed that you can get this result more or less by a composition, it's actually involves a much nicer problem, which I should mention, list recoverability. Okay, what is list recoverability as a problem? It says, look, I mean, when I transmitted some elements, beta 1, for simplicity, I'll just call it beta 1, beta 2, and so on to beta sub n. Beta sub I is in sigma, which is a letter of the alphabet. And so maybe we transmitted that, and then the noisy channel worked on it, and noisy channel says, oh, I got beta 1 tilde, beta 2 tilde, and so on up to beta n tilde. Can you recover? Okay, this is the usual decoding problem, usual list decoding problem. Okay, and you might, in list decoding, we say, okay, you won't get a unique beta 1 to beta m, but you get a list of such beta 1 to beta m sequences. But actual channels don't say, oh, a byte was written here, and here is a completely different byte. Usually what actual channels do is they say, oh, well, what I look at does not look like any of the bytes. It looks a little bit like this one, a lot like that other one, and somewhat like this. So really in list recovery, what we are going to get is sort of a possible thing saying, oh, this value could be beta 1 tilde 1 1 or beta tilde 1 2, or beta tilde 1 sub L, okay, little l. And this set, on the second coordinate, I see beta 2, 1 and beta 2, 2. On the third, I get some large set. On the fourth, I get some set, etc., etc., etc. Okay. So what we will do is the following. We'll just chop it off at some length L. And now define this problem that we call the list recovery problem. In each coordinate, you're given at most L values. If you completely miss some coordinate in your solution and you propose beta 1, if beta 1, and you suppose you get a code word beta 1, beta 2, beta 3, and so on to beta n. If this belongs to that, this belongs to that, this does not belong to it, this belongs to it, etc. You can ask the question, can you somehow recover it with few errors, where errors are considered are only these type of elements, where you completely miss? Okay. Can you recover from some fraction of errors? And the remarkable thing that happens with these codes, with the folded Reed-Solomon codes, is that as long as number of errors in the list recovery sense, which is really a weak notion of recovery. On every coordinate, you're allowed to give 10 possibilities, little l possibilities. And you say, okay, can you correct only those errors where you completely, none of these 10 things even got the right answer? Do you get a distribution? Well, okay, Rani is asking a good question. Do you get a distribution or do you get the L most probable ones? Actual channels give you distributions, and when you take that information into account, you get a problem called soft decoding, which is even more expressive than list recovery. In list recovery, we are just saying, okay, you get the top L and in no order. It's just, here are some L things. Okay, so just the L most probable ones, no order among them. What is the most sort of minimal expectation that you would have in order to be able to recover the original message? Well, there were K symbols which were important, right? At least, the message is K symbols long. So it is possible, if you look at how many of these coordinates include some message, the actual code word symbol, if that number is less than K, you shouldn't expect to correct. And list recovery power over here is the following. You can take, for every L, can solve epsilon LL list recovery with rate 1 minus epsilon minus delta. Okay, so this is a much, much stronger statement than what I proved, but the proof is more or less the same. I would just do the same proof that I had so far, and it turns out it would have solved this problem. But really, as long as there's K pieces of, K of these blobs are somewhat correlated with the original message, you are going to get the message. You can list decode it. You can solve this for every L. The capital L will depend on little l. The running time may depend on the capital L and little l, but that's it. The rest of it is actually strictly, you're going to get the right answers. So this is a very powerful tool that's available in this context. And once you have this list recovery as a tool, all kinds of nice problems get wiped out. And by the way, the only code that achieves any of these properties that we know so far is the folded Reed-Solomon code. You can decrease Q here too. Everything you want is true with constant size alphabets and so on. Yes, so the only condition that we have is if you're working over, the alphabet grows with delta and L. Okay, so you choose your epsilon, your delta, and your L. I will tell you what is the alphabet, but it'll have to be growing with L. Okay, so Q is growing as a function. So Q cannot get close to L because I choose Q after you chose an L. Great. So list recovery, I think, is an amazing thing. It's really like searching for a needle in a haystack. There's some tiny, tiny correlation between the message that was sent and what you've received, but it's just barely positive enough to be information theoretically meaningful. And there we go. We can find the message. Okay. And it's quite remarkable that this problem can be solved. And once you can solve it, it's really amazing what all we can get as tools. Okay. All right. So towards now, I might as well just tell you about what we're going to do in the next lectures. Can you do the same thing with binary alphabet? You managed to reduce the alphabet to constants. Why not go to binary? Well, if you go to binary, you should realize that the correct answer is not 1 minus epsilon minus delta. That's not the rate that's achievable. With binary codes and error probability of 50-50, you're already looking. I mean, if an adversary is injecting errors, he looks at your sequence. If it has more zeros than ones, makes the entire sequence zeros. If it has more ones than zeros, makes the entire sequence ones. That's 50% error. You're not going to, you can only transmit two distinct messages here. So you don't expect the limit to be 1 minus epsilon. Instead, it turns out now we will have to actually talk about capacity a bit more carefully. Excuse me. Sorry. Sorry about that. So how's the behavior? I mean, so we will have to look at this. What should be our target? We'll have to look at it carefully, and this will lead us to the entropy function, which we haven't really explored so far. And the next lecture will tell you all about all we want to know about entropy and Shannon capacity. What should the right bounds be over here when the alphabet is actually small? And we will be looking at the binary case, Q equal to 2 in the next 2 lectures. And we'll tell you about what are some challenges. How can you try to correct the maximum possible errors at the maximum possible rate? How close to capacity can you get? And this delta will become a very important player. And we'll give you some weak results. And in the final last lecture, we will tell you about a new family of codes called polar codes, which actually use the tools of Shannon theory to construct the perfect solution to the Shannon theory question. And the most interesting thing is all of this is all built information theoretically, but leads to beautiful algorithms as well. Efficient, fast, surprisingly fast algorithms. So that's what we will be talking about in the next 2 lectures. Okay. All right, so I'll stop here and take questions.
Yeah, thank you very much. I'll stop the recording.